As I said in the previous class, the first thing we want to do is derive an equation for how you calculate the pH of a buffer if the weak acid and the weak base are not equal. These are what are called non-equimolar buffers. I'm going to do that by starting with a problem that we did in the last class. I first asked you what is the pH of 0.1 molar acetic acid by itself. We went through the ice table and found out that the pH came out to be 2.87. I then asked to calculate the pH when you take 0.1 molar acetic acid and mix it with an equal amount of the conjugate base, sodium acetate. When we did that one, you end up with 4.74, so the pH went up because you added the acetate, which is a base, and the 4.74 is also equal to the pKa, so that's how you get the pH of an equimolar buffer. Now I want to do a problem where the starting amounts are not equal. We're going to mix 0.1 molar acetic acid with 0.5 molar sodium acetate, so that in the top row of the ice table we're starting with 0.5 acetate instead of 0.1. You're still going to shift towards the 0, so the pluses are still going to go on the right. And this time, though, you can cross out the plus x and minus x, and you will not end up with the same amount of each one. When you plug in the numbers from the last row, the 0.5 over 0.1, they do not cancel, and so you're going to actually have to solve the problem mathematically. Quickest way to do that is to multiply by the exact inverse, 0.1 over 0.5 on both sides, so then everything cancels, and you end up with x or h plus equal to a different value than it was in the previous problem. When you take minus the log, the pH is 5.44. In the previous problem, it was 4.74. The reason it went up again is that we added even more base, and so the pH had to go even higher. We don't want to have to use an ice table for this problem because, for example, if you're doing titration curves or you're wanting to graph results, you want to be able to calculate many different concentrations. And so what we want to do is get a mathematical equation where all you have to do is plug in different amounts and get pHs out very quickly. Computers like equations better than ice tables, because how can a computer do an ice table that fast? So how would you begin, though, to start to try to derive an equation for non-equimolar buffers? In all three of those problems we did, we used an ice table, but we set it equal to the Ka. So we're using the Ka expression, so that's probably a good place to start to get a formula. So I wrote the Ka expression for just a general acid, Ha losing 1H plus. And then we're going to do things with this mathematically. In math, you know you can do the same thing to both sides of an equation and it's still equal. So what we're going to do is take the log of both sides. I'm then going to write what's inside the parentheses just a little differently. I brought the H plus out in front and multiplied it by that fraction. That's the same mathematically, but now I'm able to use a property of logs. You learn this one right away if you take logarithms in college algebra, that the log of a times b equals the log of a plus the log of b. So I separated it out into log of h plus and log of that ratio. I could go one step further by taking minus the log of HA, but I don't want to do that because I want to leave the base part and the acid part as a ratio. Chemists consider that the pH of a buffer is controlled not only by the pKa of the acid, but it's very importantly controlled by the ratio of the base to the acid. And so I'm going to leave that as a ratio. If you multiply both sides of the equation by -1, you start to recognize things. Minus the log of Ka is the pKa, and minus the log of H plus is the pH. This equation, though, solves for pKa, which is not what we want to do. We can look up the pKa's. We want to solve for pH. So I'm going to rearrange. I'm adding that log term to both sides so that it switches around to the other side. That cancels out the term on the right. We want the pH on the left because we're trying to get an equation for pH. So if you just switch the sides, you get this equation which solves for pH. I rewrote that at the top of the next page. This equation that's in the box is named after two people, Henderson-Hasselbalch equation. Those names are kind of a mouthful, so I'm going to call it the buffer equation. You can use it for other things in chemistry, but our major use of it is going to be in calculating the pH of buffers. Now I want to look at the equation and see what the parts are. If you want to calculate the pH of a buffer that's not equimolar, you start with the pKa of the acid, but then you apply that log term as kind of a correction factor. And what's in it is the log of the concentration of the base part on the top of the fraction divided by the acid part on the bottom. You can write it either A minus or HA, or you can write it base over acid. Normally, if I give this test in class, this equation I write on the exam, but of course you can have it recorded when you take the test at home. I made the point here that for the concentrations of A minus and HA, because those are square brackets, you have to use molar and not grams. But because of the fact that the two are in the same solution, the base and the acid are in the same solution, they're going to have the same volume. And so the liters will cancel out, and you're also allowed to use moles. But as long as you don't use grams, you'll be fine. Now what I want to show is that under three different possibilities, I want to show that the equation works. And as you can see, the first one, I want to show that the equation gives you the right answer if the concentration of A minus equals the concentration of HA. That's equimolar. If A minus and HA are equal, you are going to get a value of 1 for the ratio, same number top and bottom. And if you take the log of 1 on your calculator, it's 0 because 10 to the 0 is 1. So that means that the pH and the pKa are equal for equimolar, which we already showed in the last class. This equation is actually used when they're not equimolar for the most part. Let's suppose that the amount of the base part of the buffer is larger than the acid part. Then what kind of a ratio would you have? Well, this is where the top number is bigger than the bottom. This is what they call an improper fraction, and the value of those is going to be greater than 1. If you take the log of a number greater than 1 on your calculator, it will always come out positive. You can try that and convince yourself using some numbers on your calculator. That means that the pH will be larger than the pKa, and that's exactly what you expect. If you use more base than acid, you would expect the pH to go up. If you use more acid than base, now the bottom number is bigger than the top, and that will be less than 1. It will also be positive, greater than 0, because there's no such a thing as a negative concentration. So these are numbers like 10 to the minus 3, 10 to the minus 7. If you take the log of a number that's less than 1 but greater than 0, that is going to come out negative. So again, we get the result we expect. If you use more acid than base, you would expect the pH to go below the pKa. That verified that the equation makes sense with examples that are not real numbers, but we want to do it with a real problem. So the problem that we did earlier with the ice table had 0.1 molar acetic acid and 0.5 molar acetate. I want to show you that you're going to get exactly the same answer using this buffer equation as you did when we used the ice table. So how do you plug this in? Well, the first thing you got to do is find the pKa. And the pKa of acetic acid is 4.74. Now you have to figure out which one is the acid and which one is the base. If you look at the one with the H on it, that's always the acid. The one without the H is always the base. So it's 0.1 on the bottom of the fraction and 0.5 on the top. I'm sure that when you do this on your calculator, you're going to enter the calculation as a complete string, so you're not going to see the 0.7. But I always write the log term in specifically because, as in this case, I want to show that it is a positive number so that the pH is going to go above the pKa when you have more base than acid. And 5.44 is the same answer we got when we used the ice table. So now we can do our problems with the buffer equation and not have to resort to writing out the whole ice table. The first kind of problem I want to do to demonstrate it is just to do a couple of plugins because that's the easiest kind you can do. First, we're going to do an ammonia buffer. This has got ammonium chloride, which is going to be the acid part, and ammonia, which is the base, and we want to calculate the pH of those amounts. In a buffer, you always have to commit yourself as to which one is the acid, which one is the base. So since Cl is a spectator here, we're going to have ammonium acid and ammonia base. Because the fraction is base over acid, the ammonia goes on the top. The pKa is 9.25. So you plug in the pKa and 0.132 on the top and 0.0741 on the bottom. It has more base than acid, so the pH goes up a little bit above the pKa. The next problem involves a sulfate buffer. So we want to calculate it when you dissolve Na2SO4 with NaHSO4. The sodium is always a spectator, so just like we discussed in the last class, HSO4 is the acid and SO4 is the base. So the SO4 goes on the top. The pKa is 1.89, shown both on page 9 and on page 10. So we put the 0.045 on the top and the 0.15 on the bottom. And because there's more acid than base, the pH goes down below the pKa. Now this is a problem where I want to show you two different things. First of all, I just want to show you by calculation that buffers work. That's important. And second of all, I want to show you that even though the pH doesn't change that much when you add an acid or base to a buffer, the pH does change a little bit. When you put H plus in, for example, the weak base does not soak it up 100% because weak bases still are only about 99% able to grab the H plus. So the more H plus you add, the less and less the buffer is able to keep the pH constant. We're going to look at what the new pH of buffers is after you add a certain amount of either acid or base. So both those things are going to be done in this problem. And I'm going to do that by constructing two solutions. One of them is going to be 1 liter of a non-buffer that starts at the same pH as a second solution, which is 1 liter of a buffer. And it's at the same pH. We're going to add H plus to both beakers the exact same amount and see how much the pH changes in each one. This is going to show you that the pH changes a lot in the non-buffer, but hardly any when there's a buffer present. I'm always going to use 1 liter for our buffers because you really don't lose that much if you use a different volume. The volumes cancel in the buffer equation anyway because the base and the acid are in the same solution. So we're just going to stick with 1 liter to make the calculations easier. Solution 1, which is not a buffer, is going to be just 1.8 times 10 to the minus 5 molar HCl. And the Cl is a spectator, so it's the H plus that's actually giving it the pH. So this is a strong acid. How do you calculate the pH of a strong acid? All you have to do is take minus the log of the concentration. So this solution is starting out at pH 4.74. The next solution, solution 2, is going to be an acetate buffer. I'm going to dissolve 0.1 molar acetic acid and 0.1 molar acetate in 1 liter. Question is, what's the pH? This is an equimolar buffer, so all we have to do is look up the pKa. The pKa is 4.74, so that's also the pH of the equimolar buffer. So this is solution 2, which is the same pH, same volume. Here's a summary of the two solutions. Solution 1 is not a buffer. Solution 2 is, but they both have the same volume and pH. The question I want to do is, what is the new pH of each solution if you add 1 ml of 12 molar HCl? The reason why we use 12 molar HCl is that is the concentrated version. All that will dissolve in water of the HCl gas, it is 12 molar, and 1 ml is such a small volume compared to 1 liter because 1 liter is 1,000 ml. So adding 1 ml is not going to be that much of a change in volume, but you're adding a very large amount of H plus because the 12 molar is so concentrated. We can't do anything in milliliters and molars, so we have to convert it to moles. So you're going to take molarity times liters. 1 ml is 0.001 liter. So we're going to add 0.012 mole of H plus to both beakers. And we already said that the volume change caused by 1 ml is negligible compared to a liter. Another reason why I'm using 1 liter is that if you do, the number of moles can be interchanged with the molarity because when you calculate moles, you're multiplying the molarity by 1. If you add the 0.012 mole of H plus to the first solution, there's nothing in there to soak it up. All you're doing is adding more H plus. So the amount of H plus that you get in there after the addition is just a sum. And I want to look at this because which of these is the amount you started with? The amount you started with is the 1.8. The amount you added is the 1.2, which means you added a lot more than you started with. You actually added 3 decimal places over, and that's how much you added compared to what you started with. That means you added almost 10 to the third times or 1,000 times more H plus, and you would expect then that you would change by 3 pH units, like the exponent. In order to get the new pH, you want to take minus the log of the amount of H plus, and the pH comes out to be 1.92, which is a very big change. We started with 4.74, went down to 1.92, so the change is almost 3 units. That's really what we expect because there is nothing to soak up the H plus in that solution 1. But if you add the same amount of H plus to solution 2, we already know what happens when you add acid to a buffer. The H plus reacts with the base part to produce the acid part. So let's look at that in terms of what the net ionic equation is. I showed this net ionic where H plus sticks to the acetate, and it says in the problem that we're starting with 0.1 of each. This is not really a nice table. It's more like a stoichiometry table, but everything is 1 in front of all the substances, so you don't really have to do mole calculations. If you add 0.012 mole of H plus, what's going to happen? Every time you add an H plus, you get rid of an acetate, because when the H plus sticks, it's no longer the negative ion. But you also, at the same time, produced another one of the acid molecules. So what you have to do to get the new amounts is you're going to have to subtract 0.012 from the amount of the base, and at the same time, you're going to have to add the 0.012 to the amount of the acid. And since this is still a buffer, what you're going to do is plug in those new amounts into the buffer equation because it's not equimolar anymore. And so we're going to put the 0.088 on the top, the 0.112 on the bottom, and the pH goes down to 4.64. If you compare that with the original, that's almost nothing. We started with 4.74, we went down to 4.64, that's only 0.1 unit. That is a very small amount of change compared to the non-buffer, and the thing is there was something in this solution that did soak up the H+. That was the buffer. One of the problems people have understanding how to do this problem, though, is they don't always understand why you're supposed to subtract from one and add to the other. I came up with a visual method of trying to show that, and I want to show that on the next 2 slides. So I hope this helps. In order to show this, I invented a new kind of a figure called a circle square. So we're going to start with a mixture of 4 circles and 3 circle squares. And we're going to add 2 squares and see what happens mathematically. What you have to understand is that squares and circles are really hot for each other. As soon as one sees the other, they immediately join, "I love you," and they stick together to make a circle square. So what's going to happen here is that you are actually going to form 2 new circle squares, and you're going to get rid of 2 circles. So let's see what happened mathematically. You started with 4 circles, you lost 2 of them, so you now have 2, but at the same time you started with 3 circle squares and you added 2, so now you have 5. This is the reason why you have to subtract from one and add to the other. Now just pretend like those 2 blue squares are H pluses, which is what we're doing in the real problem. This leads to a rule which you can do it by using the stoichiometry table, but if you understand how to use this rule, you don't really have to do that. The thing about it is that when you add an acid to a buffer, you're supposed to add to the amount of acid and subtract from the amount of base, then plug into the buffer equation. The way you read this is when you add an acid, you add to the acid and subtract from the base. I think that's a pretty easy way to remember it, and I want to show you that that's actually what we did. When we added acid, 0.012 moles, you can see that we added to the acid and we subtracted from the base. And then you plug in the buffer equation to get the new pH. I drew these columns last class. If you start with equimolar and you add H+, the amount of acid goes up a little, the amount of base goes down a little, and they go up and down by exactly the same amount. So the summary of this first problem is that when you added the H+ to a non-buffer, the pH went down almost 3 units, but when you added it the same amount to a buffer, the pH only went down by a little dink. It's just 0.1 unit, which is almost nothing, because the H+ got soaked up. I think you could figure out that when you add base to a buffer, it's going to be the exact opposite what you do. When you add base, you add to the base. And you have to also remember to subtract from the acid before you plug in. We're going to do an example of that. We're going to use an ammonia buffer where we start with 0.25 molar of the acid, ammonium, and 0.12 molar of the base, NH3. It's always in a volume of 1 liter. So I want to calculate the pH that we're starting with, and then I want to calculate the new pH after you add 2 grams of sodium hydroxide solid to the buffer. So is this, first of all, going to change the volume much? This is a picture of what sodium hydroxide actually looks like. You really can't crystallize it because there's too much carbon dioxide and water, and it comes in the form of pellets. Probably a few of these pellets would add up to 2 grams. And since they're so small, putting them in an entire liter of water is hardly going to change the volume at all. But this is a very concentrated form of OH. So you're actually adding a lot of OH without really changing the volume much. We've already looked up lots of times now that the pKa of ammonium ion is 9.25. In order to get the original pH, we're going to plug in 9.25, and we're going to plug in 0.12 for the base on the top and 0.25 for the acid on the bottom. So our starting pH is below the pKa, 8.93. Now you're going to add the 2 grams of sodium hydroxide. The grams doesn't help because the problem comes in moles. We have to convert it to moles. In analytical chemistry, everybody likes sodium hydroxide because the molar mass is exactly 40, 1 sodium, 1 O, and 1 H. And so if you divide, we're actually adding 0.05 mole of OH. Even though sodium is going to be a spectator when you get it in the solution, you have to include it in the mass because it's part of the crystals. When you add OH to a buffer, you know that it reacts with the acid part of the buffer, which in this case is ammonium NH4+. So we can make another one of those stoichiometry tables. This time, the net ionic equation has OH pulling an H off the ammonium. We're starting with the amounts 0.25 and 0.12, and we're adding 0.05 of the OH. Every time the OH pulls one of the H's off ammonium, you get less of it, and at the same time you produce more of the NH3. So when you subtract from the acid and add to the base, these are the new amounts you get. And you plug the new amounts, base on the top, acid on the bottom, and it comes out to 9.18. So the pH is still below the pKa, but it didn't change anywhere, but it didn't change very much. If you subtract those two, the absolute value of the change is only 0.25 unit. If you were a chemist, you would probably say the solution started at pH 9 and it's still pH 9. I want to show you what we did, that we actually did follow this rule. So when we added base, we added to the base, and subtracted from the acid. This time, if you look at the columns, when you add OH, it's the base that goes up some, the acid goes down some, and they go up and down by exactly the same amount. In the first problem we did, we had a non-buffer and a buffer, and we added the same amount of acid to each one. I want to do the same thing with this problem to compare how much would the OH change the pH of a non-buffer, but I didn't tell you how to make the non-buffer, so I want to think through the process. How would you get a pH 8.93 solution to start with? The steps to this are on page 197, but I'm going to draw pictures so we can see it easier. In order to make a non-buffer that pH, you have to do the conversion we've been doing all semester. You have to convert pH to OH, because you know that when you're above 7, you're going to have to add OH to get the pH 8.93. Most people will do this by taking 14 minus to get the POH, and then they take the second log of negative POH to get the OH. So if you make a solution of that concentration of OH, it's not a buffer, but it is pH 8.93, just like the pH of the buffer from the earlier problem. And here it is summarized on 197. The next thing you want to do is calculate the new pH after you add 0.05 moles of OH. When you put in the OH, there's nothing in there that can soak it up, so all you're doing is adding more. When you get it this time, there's even more of a difference between what you added and what you started with than there was in the acid problem when we added it. This time, you added 4 decimal places more. So this time you would expect the pH to change by almost 4 units. In order to find out what the new pH is, we have to take that new amount of OH and convert it back to pH. If you take minus the log of the OH and then 14 minus the POH, you find out that the pH went all the way up to 12.7. That is an absolute value change of almost 4 units, which is what we predicted. So here's the summary of the problem. We took a non-buffer and a buffer at the same pH. We added the same amount of base to both. The non-buffer changed by almost 4 units, and the buffer changed by only 0.25. Another way to say that is you added enough OH to make the pH change almost 4 units, but the buffer stopped that and only let it change 0.25. Now what I do when we're doing these problems in class is I will give students a page that has these 3 problems on it, and then I will give them time to do the problem themselves so they can follow the steps that we just did. You can do that by looking at the problem and then just pausing it and seeing if you can get these 3 by doing it yourself on paper. If you do that, you can see if your answer is right, and then we're going to go over it after you do that. What the problem is you're going to start with a buffer of HF and F minus, the number of moles I show, and we want the pH. Then you're going to add 0.04 moles of OH, and you want the new pH. Then you're going to go back to the original buffer and add 0.03 moles of H plus and see what the new pH is. This is how I usually give these problems. I'll usually draw a picture, and I usually give it in moles. I don't make you do grams to moles or milliliters and molar and all that stuff. I'll just give you how many moles you start with, how many moles you add. So all you have to know is which one do you add to and which one do you subtract from. So we look up HF, and you can see that the pKa is 3.15. In order to get the original pH, all we're going to do is take the buffer equation, plug in the base 0.07 on the top, the acid 0.13 on the bottom, and the pH goes below the pKa. When you add base in part B, when you add a base, you add to the base. Since the F minus is the base, you're going to take 0.07 plus 0.04 and subtract from the acid. So you're going to take 0.13 minus 0.04 and get the new amounts. Once you do that, you then take the base part, 0.11, put it on the top, the acid part, 0.09, put it on the bottom, and the pH went up a little. The thing is, what people say is, why didn't I have to use the original pH, 2.88, in order to get this? The reason is that it's not the original pH that has anything to do with the pH after adding. What it is the pKa. The thing that changes the pH is actually the base to acid ratio. So you're going to start with the pKa anyway. All you want to get is the new amount of acid and the new amount of base, and that tells you what the new pH is going to be. If you take the absolute value of the pH change here, you're changing by about 1/3 of a unit. If you can keep the pH from changing by less than half a unit, you're doing pretty good with a buffer. In the last part of the problem, you're adding acid. So when you add acid to a buffer, you add to the acid and subtract from the base. So since the acid is HF, we took the 0.13 and added H to it. F minus is the base, so we subtracted the H plus from it, and you plug in the new values, 0.04 base on the top, 0.16 acid on the bottom, and the pH goes down some. But it only goes down about 1/3 of a unit again. So this shows that the buffer has been pretty effective. Now in this class, we have to do a section on indicators because this is a big part of acid-base chemistry. I think you're familiar with phenolphthalein because most people have done the titration where you have an acid with phenolphthalein dripped into it in a flask, and then you drip sodium hydroxide into it from what's called a burette. It has a stopcock on it, so you can let in a drop at a time. You keep adding the amount of base from the burette until it exactly equals the amount of acid in the flask. And the way you can tell when they're equal is that the indicator, which is colorless in an acid, turns pink or magenta in a base, and 1 drop will make the pH change. Then you could calculate how much acid it was in the flask from how much base you added. Phenolphthalein is not the only indicator. There are probably 100 of these things in the Handbook of Chemistry and Physics. They can undergo all kinds of color changes over a huge range. They go all the way from 0 up to 14. If you want an indicator that changes from 12 to 14, it's called picric acid, and it kind of explodes like dynamite. So if you have to use dynamite for a pH indicator, I would give you some advice. Buy a pH meter. But anyway, these are all different indicators. They change color over a whole huge range. And depending on what pH you want to detect, you have to use an indicator that's appropriate for that pH range. I did this in the lab, and I'm going to show you pictures of it. But the thing is that if you start with the problem that we did first, you can make a solution that's not a buffer and another one that's a buffer and add the H plus to it. We want to show how the pH changes, but by using an indicator. The indicator I picked is methyl orange. A lot of indicators have colors that are something followed by a color, phenol red, brome cresol green, things like that. What methyl orange is it's an indicator that is red below 3.2 pH. That's the acidic color. Above 4.4, it's yellow, which is the acid color, and in between, it's a mixture of red and yellow, so it's orange. That's why they call it methyl orange. The thing is, why does it change color and over what range? We're going to look at that. All an indicator is just a weak acid. They have very complicated formulas, so I did not put this in the weak acid table, but I could have. It's a weak acid that loses 1 H+. The difference in an indicator from the ones we were looking at is that they have two different colors depending on whether the H is attached or not. So in methyl orange, when the H is attached, it has a red color. When you take the H off, the color changes to yellow. You can explain in organic chemistry how you can get a color change like this just from losing an H, but that's kind of an organic chemistry topic, but it happens all the time, and it's really not that difficult to explain. Because the methyl orange is a weak acid, you can get a Ka value. You're going to get a Ka value for an acid in the lab, and so you're going to do it in a method similar to this, but you can also get the pKa then minus the log of the Ka. You know that when you have an equal amount of the acid and base, that's equimolar, the pH equals the pKa. And I showed the 3.47 where it is in the color change range of methyl orange. You remember that the range that a buffer can maintain is plus or minus 1. So indicators will have a color change range around the pKa of about plus or minus 1, but it's never that big because it also depends on how your eye sees color. The 3.47, when you have equal amounts, it's still going to look pretty much red to your eye because red happens to be a stronger color to your eye than yellow. You really need like a 2-to-1 ratio of yellow to red to really get orange. So that's why the pKa is not right in the middle. We can still use this indicator for the problem because both of our solutions started out at pH 4.74, which is in the yellow range. The one that was not a buffer went all the way down to 1.92, so you would expect it to turn red. The one that was a buffer only went to 4.64, which stays in the yellow region, so you wouldn't expect it to change color. And this is going to show that buffers actually do work by preventing that color change. This is an experiment I did in the lab. I started with a pH 4.7 solution with methyl orange in it on the left, and I adjusted it with a pH meter. And then what I did was added 1 ml of 12 molar HCl per liter. You can do this with an automatic pipetter. You're doing it in the lab with a graduated plastic pipette. Anything that measures volume will allow you to do this. When I put it in, at first the place where the acid hits turns red because there's a local excess. And when you stir, the red color stays all throughout the flask because there's nothing in this non-buffer to soak it up. But then I made an acetate buffer. I put in enough acetic acid and sodium acetate to make 0.1 molar each, and the pH adjusted to right around 4.7. And then I added the acid, the same amount, to this beaker. It still turned red right where it hit because there's a local excess of H+, but as I stirred, the red swirls kept disappearing because the buffer kept neutralizing it, and by the end, the color had not changed because it only changed pH a little bit. I decided to do the same experiment with the second problem we did, where you started with pH 8.93 in both of the flasks. We added OH, the same amount, to a non-buffer and also to a buffer, and we found out that the non-buffer changed by almost 4 units, the buffer changed by only 0.25. I needed an indicator for this experiment that changes around pH 10, but I did not know one. I tried phenolphthalein, that changes around 9. It just didn't work. It was pink the whole time. So what I did was look up in the Handbook of Chemistry and Physics. There's a whole list of these, and I found this one called thymolphthalein. A lot of times indicators end with the name phthalene, like phenolphthalein. This particular one, it said, has a color change where it's colorless below 9.4 and blue above 10.6. And so I never heard of it before, but I went to Fisher Scientific Catalog, and there it was. You could buy bottles of it already made for titration for a pretty cheap price. So I bought a bottle. In the experiment, both of the flasks, started at 8.93, which is in the colorless range. When we dissolved the sodium hydroxide in the non-buffer, the pH went all the way up to 12.7, which is obviously going to turn it blue. But when we added the same amount to a buffer, it stays at 9.13, it stays in the colorless range. So I took a picture of this. The beaker on the left, I adjusted to as close to 8.9 as I could with a pH meter, and it had thymolphthalein in it. The beaker on the right, I put in 2 grams of sodium hydroxide per liter. When I started to stir, you could see blue swirls coming out of the sodium hydroxide solid, but the thing is, it just kept getting bluer and bluer and filled the whole flask because the pH went all the way to 12.7. But then I made an ammonia buffer, which had the concentrations that it said in the problem. In order to do the 15 molar ammonia, which is what you buy, and get it all the way diluted down to what was in the problem, you had to do serial dilutions. And anyway, when I did dilute it and added also the solid ammonium chloride, the pH is around 8.9, and so it's colorless. When I dissolved 2 grams of sodium hydroxide in that buffer, you could see blue swirls coming out from it, from the solid, but they kept disappearing. And after all the solid was dissolved, it was still colorless because although the pH changed a little, it didn't change enough to get out of the colorless range. So I hope by these you can see that buffers really do work. And you're going to do an experiment in the lab that's using buffers, so hopefully you'll see for sure then how effective they are if you make them right. This is just a reiteration of the fact that you can pick indicators at all different color change ranges. At the end of this lecture, we're going to talk a little bit about titration curves. You're going to see why you want different indicators for different purposes. One of the purposes that I wanted to mention for biology, though, is that the phenol red is one of the indicators that they put in agar plates. And in the carbon dioxide atmosphere in an incubator, the phenol red is going to be red. But if you put bacteria on the plate, if it's an acid-producing colony, you'll see a little yellow circle forming around the colony because the acid from the bacteria is changing the color of the phenol red, and they use this to identify acid-producing bacteria. So I just thought that was an interesting application. That's a biology application of an indicator. Now, this is another kind of problem I want you to be able to do. Let's suppose that you do an experiment that requires a buffer of a certain pH. This experiment, let's say we need a pH 10 buffer. Well, if you remember, we said that in order to get a buffer of that pH, you have to pick an acid that's got a pKa between 9 and 11, because that's the plus or minus 1 range. But I decided that I'm going to use an ammonia buffer because I want to do problems where everybody gets the same answer. I want to ask the question, first of all, what base to acid ratio will we need to get pH 10? That's what a chemist really wants to know. If you can get the base to acid ratio in a buffer that gives you a certain pH, that means you can use a lot of each one or very little of each one, and as long as they're at the correct ratio, the pH you get will be 10. The second problem I want to ask is very realistic. Let's say that you know how much of the base you want to start with, 0.15 molar ammonia. This question says, how much of the acid part do you need to give a pH 10 buffer? So we want to do these two and do it by the buffer equation. We've looked at a lot of times now that the pKa of ammonium ion is 9.25. So what you want to do first is you want to plug in the 9.25 for the pKa, and then you want to leave the ratio with ammonia on the top, the base, ammonium on the bottom, and the ratio is what you want to solve for. In other words, if you wanted to replace the ratio itself with an x, you would be having log of x. That's what you want to solve for. And so how'd you go about that? First thing you do is subtract 9.25 from both sides to get the log by itself. The 9.25 cancels, and I put the log on the other side because it's got the variable in it. And if you take the difference on the other side, it's 0.75. And so we got to solve this equation. Between now and the end of Chem 132, we're actually going to do this exact same log equation 4 times. We're going to solve it in buffers, in kinetics, in thermodynamics, and in radiation, radioactivity. So you got to learn how to solve this one equation. But it's not that bad, because if you want to get rid of the log, you cannot throw it in the fireplace and burn it up. It's not that kind of log. What do you have to do? If you want to get rid of a function in math, you have to take the inverse function. So you're going to take the inverse log of both sides. When you take the inverse log of a log, it cancels out the log. But you also have to do the inverse log of the other side. And you know what an inverse log is from doing pH problems. Anytime you hit second log, it comes out to be 10 raised to the power. The only caution I have to give you in this kind of a problem is that you do not want to stick in a negative then in front of the 0.75 like you do when you're doing pH problems. This is not a pH problem. This is solving for a variable. So if the number comes out positive, leave it positive. If it comes out negative, leave it negative. So now you know what the ratio is, and anytime you keep NH3 and NH4 in that ratio, 5.62, you will get pH 10. What part B in the problem says, if you already know that you want to start with 0.15 ammonia, what concentration of NH4 plus do you need in order to get the pH 10? The problem is, in solving this equation, I see students that get any of the 3 possibilities: 0.15 times 5.62, 5.62 divided by 0.15, or 0.15 divided by 5.62. Obviously, it can't be all 3 of them, because it's only one answer. I don't care how you do this problem as long as it comes out correctly, but I want to show you a very definitely idiot-proof method that will always get you the right answer. If you multiply both sides by the concentration, you'll cancel the NH4 plus. And I switched the 2 sides of the equal sign, so the variable's on the left. Then you can divide by what's next to the variable. No matter how you do this, as long as you get 0.15 divided by 5.62, doesn't matter how you got there, that is the correct answer. So that means you want to use 0.027 molar of ammonium. And the idea is that if you mix 0.15 ammonia and 0.027 ammonium chloride, you should get a pH of 10. Now, people ask this question of me every year, though, and I want to answer it. What if all I had asked in this question was part B? I did not ask you to get the ratio. See, a chemist will usually get the ratio because once you have it, you can calculate all kinds of buffers with it. But if I did not give it to you and all I asked you was part B, people ask me, can I plug in the 0.15 right away and then solve? And of course you can, because it's just a math equation, but you're going to get exactly the same answer, because what you're doing is you're now plugging in the 0.15 before you solve. So you're still going to subtract 9.25 from both sides and then take the inverse log. This time when you get rid of the log, you're just not going to see the ratio this time because it's already plugged in. But the answer is going to come out exactly the same. Even though you expect to get pH 10, a lot of times the pH does not come out. It usually comes out a little lower, even if you do the calculations very carefully and weigh very carefully and everything else. And I think at least part of the reason is this. If you leave tap water sit out, the pH of tap water is not 7, as you would expect it to be. It's more like 5.5. And the reason is that carbon dioxide from the air can dissolve a little bit in water, and it produces carbonic acid, which gives the solution acidic pH. The thing is, I think you're fighting this when you try to make a buffer, and it sometimes drags the pH slightly lower. The other problem in a buffer is that it's not necessarily that the pH is even close. Maybe you have a buffer made and the pH is off by quite a bit. Rather than having to start over and make a new buffer, there is a way to do it in an alternate manner, which is the way they really do it, probably in clin labs and research labs. This is a big part of what you do. You can make a buffer by this alternate method. It's to adjust the pH to what you want. I'm going to show you the most exaggerated case where you start with a solution of either the weak acid or the weak base by themselves. You don't have to start with it by themselves. You just have to start with one that has the wrong ratio, so the pH is wrong, but this is the extreme. What you can do in this case is you can put a pH meter first into the solution, not the meter, an electrode from a pH meter. Remember, a pH electrode has a glass bulb on the bottom that's sensitized to H+, and you can read out the pH. If the pH of your buffer is too high, you can add a strong acid like HCl, and it will bring the pH down until the pH is correct. If you have a pH that's too low, you can add a strong base like sodium hydroxide to bring the pH up. I'm going to show you that you are actually not using a strong acid or a strong base as part of the buffer. What you're doing is you're adjusting the pH of the buffer by changing the ratio of the weak acid and the conjugate base until it's correct. You're not actually making a buffer out of the strong stuff. And as you add the acid or base, you can stop when the pH says exactly what it should, and then you correct for all the errors. This is an example. Let's say that I wanted to make a buffer of pH 10 from ammonia only to start with. You can put in the pH meter and have a magnetic stir. What that is, you're going to use that in organic every experiment probably. It's got a magnet inside that goes around when you plug it in the wall, the magnetic stir, and then you put a Teflon coated magnet inside the beaker, and the two magnets move together, and you can stir the solution mechanically as long as you want to. So the first question I want to ask is, what kind of a pH will you get if you have only NH3? Well, you know that NH3 is a weak base, but you haven't added the acid part yet. So you're going to get a pH that's in the basic range, and not only that, but it's going to be above 10 because you didn't add the base part, or you didn't add the acid yet. One way you could adjust the pH is to add the NH4 plus part, but that's usually not too good because a lot of times it dilutes the buffer too much, so the volume goes up. You want to add a concentrated form, and so since the pH is too high, you can add a strong acid, HCl. What happens when you add the HCl, you're not making a buffer out of the HCl. What happens is the NH3 that's in the solution soaks up a little bit of the H+, and it generates right in the beaker the other component that you need of the buffer. So the definition of the buffer hasn't changed. It's still a weak acid and the conjugate base. It's just that you use the acid to generate the other component of the buffer in situ, or in vitro, as they say, right in the beaker. And then you can stop as soon as the pH meter says 10, and your buffer is corrected for any errors. I had to call this something so I could ask questions about it. Probably nobody else is going to use these words, but the concept is exactly the same no matter where you are. I'm going to call this NH3 with slowly added HCl. Whenever I use the word slowly added in this class, it means a drop at a time, a little at a time, and then you look at it after each drop and see what happens. And so I'm always going to use HCl as the thing I add, and this is one alternate way to get the buffer. What if I wanted to start with only the NH4 plus part? What kind of a pH would that give me? Well, NH4 plus is a weak acid, and so you're going to start with an acidic pH. The pH is probably going to be around 5, and so you want the pH to go up to 10. You could add the ammonia part, but more than likely people are going to add a strong base, most typically sodium hydroxide. What the sodium hydroxide does is it pulls a few of the H pluses off of the ammonium and generates the other component of the buffer that you need, NH3, right in the beaker. So the definition is still the same, a weak acid and the conjugate base, but you're using the OH to generate the other component. And then you can stop at pH 10 again and your buffer's just right. This one I call NH4 plus with slowly added NaOH, and I will always use NaOH as the strong base. When you're doing this alternate method, there's two combinations that work. You can start with a weak base and slowly add HCl, or you can start with a weak acid and slowly add sodium hydroxide. You can't add two bases, that's not going to give you the acid part, and you can't add two acids, that's not going to give you the base part. But if you use these two combinations, this is alternate for making a buffer. I just wanted to show you why else might you want to adjust the pH of a buffer. There might be other purposes. This is a pig heart. The very first experiment that I had to do in biochem, believe it or not, was we had to isolate an enzyme from pig heart. If you stayed for that experiment, you probably were going to stay in grad school, otherwise forget it. But anyway, this is biochem. This is how it's done sometimes to isolate things directly from tissue. They brought us a pig heart from the slaughterhouse. And what we had to do was make a buffer first, and then put the pig heart and the buffer in a blender and puree the heart. You then take that heart soup and pour it into cheesecloth, and you squeeze the liquid out of the cheesecloth into a beaker. There's still snot left in it, mucopolysaccharides they're called, and so you centrifuge to get the snot out, and then you save the liquid. And that has the enzyme in it. And then you can take the solution and purify the enzyme from it by all kinds of methods, columns, and all kinds of things. But after you homogenize a pig heart in buffer, do you think the buffer is still going to have the same pH as what you made? If it does, it is a miracle. So if the pH went up, you add acid to bring it down. If it went down, you add acid to bring it up. This kind of thing happens in science all the time. This is an example of where they use it in an industry. These artificial tears are very important because a lot of people have lacrimal ducts that don't produce enough tears, and people can actually go blind from the eyes drying out. I know this was a big problem. Both of my parents had Parkinson's disease, and Parkinson's is one of the conditions where you get dry eye. And so I was always putting drops, especially in my dad's eyes. The thing is, if you look very closely at the inactive ingredients, I don't know what pH drops are supposed to be, 6 point something for your eyes. I don't know. But there's a statement in the inactive ingredients that says hydrochloric acid and or sodium hydroxide may be used to adjust pH. Wow, that's exactly what we just did. If you're in an industry, they have what they call automatic titrators. You can put a big pot of the tears right in a container and a pH meter. If the pH is too high, they automatically drip in just the right amount of acid. If it's too low, they drip in the amount of base. After the pH is adjusted, out it goes. You bottle it and bring in the next batch. So this kind of thing is actually used in real applications. I'm going to do another problem with a different buffer. I want to make a pH 3 buffer out of the acid HCHO2, and you can replace the H with a sodium to make the base. This is what's called formic acid. And I want to determine what base to acid ratio you need to give you pH 3. And then I want to calculate this time the amount of base you need to go with an acid to make the correct pH. So this is going to be kind of the upside down of the problem we did with the ammonia. Formic acid was originally isolated in organic chemistry from ants. I already showed you how some of the biochem is done. Now you're going to find out how the old-fashioned organic chemistry worked. They don't really do this exact kind of thing anymore. They synthesize stuff, but it was originally, the prefix form means ant, and formic acid was originally isolated from what are called fire ants. These are little suckers that live south of the Mason-Dixon line. I guess it's too cold for them to come up north, so they have to stay in the south, because if they come up north, they freeze their little blankies off. But anyway, they have to stay down south. But you don't want to get near these things because they will bite you, and the bites hurt very badly. Almost everybody knows about it who is from the south, Alabama, Texas, Mexico. They have fire ants in all these places. I go to Alabama all the time, and you learn very quickly to watch for these kind of hills. I usually wear long pants in Alabama, whether it's hot or not, because they have two things there: snakes and fire ants and ticks. I guess that's three things. You don't want any of them. So if you wear long pants, there's less of a chance of things getting you. But if you step on one of these ant hills and the fire ants crawl up your leg, that is a bad situation. This is a picture of a fire ant biting somebody. What they do when they bite you is They basically have a head full of formic acid and probably some venom. But what they do is they inject formic acid under your skin. And I'm telling you, formic acid is very corrosive. It makes you, it hurts, and it burns very badly. This is a picture of a guy that got fire ant bites all over the back of his hand. It doesn't look like fun, and I never got bit by one yet. I'm probably gonna, but they say it's not fun. You're going to use an apparatus that looks very similar to this in organic chemistry when you distill things. You're going to do it usually microanalysis, though this is large ones for a lot of stuff, but it looks very similar. What it is what they did to isolate formic acid initially is they took a round bottom flask and filled it with fire ants. Now, I don't have any idea why it's a Florence flask. I don't know who Florence was, and I don't know why she had a round bottom, but everybody has their problems. Anyway, you put in fire ants and basically cook them up. I suppose the first thing you get is ant popcorn. You get pop, 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 pop. And then pretty soon the ants start to boil. Does this sound like fun? And the vapor goes up into that distilling tube and it condenses after it gets off the heat, and it drips down into the second Florence flask. The only thing that really distills off of ants is formic acid and water. The rest of it is mostly solids. So you can get a formic acid solution isolated. I forgot to say from the last slide, I don't want to know what was left in the beaker or in the flask, and you're going to find out about that in organic, because when you distill something, you're always left with brown glop or black glop. You can compare your glop to somebody else's and see whose you think is the most attractive. But anyway, thank goodness they don't do organic chemistry, hopefully too much, by boiling animals anymore. But anyway, it was done that way at one time. Now let's finish this. Let's do this problem. We want to find first the base to acid ratio that will give you pH 3. The pKa of formic acid is 3.77, so buffers made with it are going to be acidic. So the way you plug this in is that you want to get a pH of 3. The pKa is 3.77, and the base on the top and the acid on the bottom. You're going to subtract 3.77 from both sides. This time when you subtract, you get a negative number on the right. This time when you take the inverse log of both sides, make sure that you leave the negative that's in front of the 0.77. If there's a positive there, leave it positive. If there's a negative, leave it negative, because you're solving an equation this time. And when you do this calculation, you get 0.17. The part B says if you start with 0.6 acid on the bottom, how much base do you need? Well, this is easier because all you got to do this time is multiply both sides by 0.6. So if you multiply both sides by 0.6, it cancels out. And you end up with that if you end up with 0.1 molar, so if you make a buffer of 0.6 molar acid and 0.1 molar base, you should have pH 3. You probably won't get it exactly, and so, but you can calculate it. We're going to look at how to do it alternately in a minute. If I had not asked you for the ratio, you could have plugged in the 0.6 right away, just like we did in the other problem we looked at with the ammonia. The only difference is you will not see the ratio. The 0.6 will already be plugged in, so you can just solve directly. You can make this buffer by the alternates the same way we did with the ammonia. You can either start with the weak base part of the buffer, sodium formate, and slowly add HCl, or you can start with the base part, with the acid part, and slowly add base. If you start with only the base, here's the pH meter. You're going to get a basic pH initially, so you have to add HCl to make it come down. The H plus sticks to the formate, and you get the other component of the buffer, and you stop when the pH is 3. This is what's called this is what I call CH2 minus with slowly added HCl. The other way to do it is to start with the pure acid, and then you can add sodium hydroxide to make the pH go up, because the pH is going to be less than 3 to start with because you didn't add the base part yet. The OH pulls an H off the acid and gives you the base part of the buffer, and when you get to 3, the ratio is perfect. So you would call this HCHO2 with slowly added NaOH. I want to do a couple of these problems just to ask you the way I ask on tests and things, will the following produce a buffer? And just because it says slowly added doesn't mean it's always going to work. So will you get a buffer if you start with HClO2 and slowly add HCl? You're not going to get a buffer this time because these are both acids. Where are you going to get the base? So you can't put two acids together and get a buffer. Now what about NaCN with slowly added NaOH? Well, you know NaOH is a base, and so is CN minus. There it is on the right of the arrows. So if you add two bases together, that's not going to make a buffer either. But ammonia with sodium hydroxide, that's no good either because these are both bases. Again, ammonia is a weak base. Sodium hydroxide is a strong base. That's not going to work. So we still don't have one that works. Let's try the next one. If you take acetic acid and slowly add NaOH, now we're going to get one that works because you're taking a weak acid and you're adding a strong base. So you are going to be able to use that to make a buffer if you wish. What's actually going to happen when you make that buffer? Why does it make a buffer? When you start with the weak acid and start adding OH, the OH is going to pull off a few of the H's from the acetic acid, and you're generating the base part right in the test tube, and you can stop when the pH is just right. The next one asks, NaClO with slowly added HCl. Well, NaClO is a weak base, or the ClO minus part of it is. So if you take a weak base and add a strong acid, it should work. Let's see about that. Here you can see ClO minus really is a weak base. How is this actually going to work? If you start with ClO minus and you add an acid to it, the acid is going to stick to the ClO minus, and it's going to generate the other component, the weak acid, right in the test tube. And you stop when you get the correct pH. The last thing I want to discuss is going to lead into titration curves. This is the topic of buffer capacity. Now just think about it. We showed how little the pH changes in a buffer if you add a strong acid or a strong base to it, but that's only if you just add a little. Doesn't it make sense that if you keep adding a strong acid to a buffer, it's not going to continue to prevent the pH change forever because everything wears out after a while? The way to define capacity is normally pretty easy. If you want to determine the capacity of a glass for liquid, you just fill it with water all the way to the top and measure the amount of water. That's the capacity. The thing about a buffer is there's no absolute cutoff. So I'm describing the buffer capacity in a way that makes sense to me. It's the amount of acid or base that the buffer can hold without the buffering ability being destroyed. In other words, it's the total amount of acid or base you can add and still have a buffer. I'm going to use the example of the equimolar acetate buffer to demonstrate this. Let's say you have a buffer with 0.1 mole each of acetic acid and sodium acetate. We've already looked at the net ionics for this buffer soaking up acid and base. The base part soaks up the acid and the acid part soaks up the base. Looking at this in the columns, I showed what happens to the acid and base when you add. Now the thing is, what if you don't stop here though? You keep adding acid. If you add a little bit of acid, you're fine. You just changed it a little and you're ready to add more without the pH being different. But now you add more. It's probably still a buffer, but you're starting to use up the base part. Now you add even more. Can you see what's going to happen eventually? Eventually you're going to be able to add enough H plus to completely get rid of all the base. You don't even have to completely get rid of all the base for it not to be a buffer anymore. And I want to show that with a graph in a minute, but let's look at something else first. Let's say that you started with the buffer we talked about, 0.1 mole of each. But then all of a sudden you added 0.3 mole of H plus. What's going to happen? If you add 0.3 mole of H plus, that's more than the amount of base there is to soak it up. So you're not only going to get rid of the 0.1, you're also going to have some left over. Obviously, there wasn't enough of the buffer to soak up all the H's, and so it didn't have a sufficient capacity. This is a graph that demonstrates what happens when you start adding acid and base to a buffer. The pH is on the y-axis. In order to understand the x-axis, you have to think about what they're doing. The 0 point is when you haven't added anything. So if you have an equimolar acetate buffer, the pKa and the pH are 4.74. If you start adding OH, though, if you're going up, that means you're becoming more basic. H plus goes down. When OH goes up, H plus goes down. So you're really adding them in the opposite direction. Now look at what happens when you start to add. We've already done these problems. You can make a graph of this by saying, what is the new pH after you add 0.01 mole of OH, then 0.02 moles, then 0.05 moles, and you can get a graph. What happens is the pH changes very little at first, but eventually, as you get to the point where you've used up almost all the acid, it's not going to serve as a buffer anymore, and there's a point where the curve goes up almost vertically. So it's not a buffer anymore, because if you add even one drop, you change the pH dramatically. There's no absolute cutoff for this. There's only one inflection point on this graph, and that's actually right at 0. But for most people, what they use is when you get to a base to acid ratio of 10, in other words, you end up with 10 times more base than acid, the thing is not really a very good buffer anymore. And the same thing happens in the reverse direction, adding acid. When you get to the point where you have 10 times more acid than base, you can consider that that's not really a buffer anymore. This is where the buffering range comes from. Because if you take the log of 10, the log of 10 is 1. So at the place where it stops buffering, the pH equals the pKa plus 1. So you can go up that far. The same thing happens in the reverse direction, because the log of 0.1 is -1. So this is why people say the approximate buffering range is plus or minus 1 pH unit. It's not exact. Depends on where you want to cut it off, but this is a pretty good rule of thumb. What you can use this for is to determine how can you make a buffer better. In other words, if you have a buffer that doesn't have a sufficient capacity, What things can you do to make the capacity better? Well, the first one is pretty obvious. If you use more of the weak acid and weak base at the beginning, it is going to be able to neutralize more H plus and OH. Let's say that in that acetate buffer we looked at before, instead of starting with 0.1 mole of each, you start with 0.5 mole of each. If you add 0.3 mole of H plus to that buffer, you're going to add to the acid and subtract from the base, but because there was more base this time, you still have base left over. So this is still a buffer. You did not destroy the buffer capacity this time with the 0.3 H plus. The other possibility comes from the fact that if you look at the graph, where does the pH change the very least? It changes the very least when the buffer is equimolar. In other words, when you haven't added anything. So that means an equimolar buffer is the best possible buffer. So in order to make the buffer the best you can, you want to pick an acid that has a pKa as close to the pH you want as possible. In other words, if you want a pH 9 buffer and you have two acids that you could use, one is 9.2 pKa and the other one is 9.8, other things being equal, you're going to pick the one with 9.2 because your buffer is going to be closer to equimolar. The thing is, both of these are restricted by the requirements of your experiment. You want to use as high a pH or as high a concentration of the original buffer as you can, but it can't be too high. I mean, if you destroy your experiment by using too high a concentration, that's no good. So you try to maximize it based on your experiment, and the same with the pKa requirement. Maybe, for example, you're culturing cells, but the acid that would be closest to the pH you want is actually toxic. Well, you can't put toxic stuff on your cells. So it has to be based on the requirements of the system that you're doing. But this is the general guidelines for trying to make a buffer better. These kind of graphs are actually used in analyzing titrations. If you take analytical chemistry as a chemistry major or a biochem major, I know that the first experiment they do, and because I've seen this done with other people that went on, the first thing they usually do is they have you graph a titration curve using Microsoft Excel because it has graphing capability. And so I want to show you kind of what you're talking about. We're not going to do it mathematically, but I'm going to do it in principle. One of the indicators that's used in this example is phenolphthalein. The other one is methyl red, though. Methyl red has a red color in acid and a yellow color in base. Let's suppose first that you want to titrate a strong acid with a strong base. The NaOH is going to be in the burette, and so the amount of HCl is what you want to measure. When you do a strong neutralization, we talked about the fact that when you get to the point where they're equal, which is called in a titration the equivalence point, because NaCl is a neutral salt, you are going to have a neutral pH. This is a graph of the pH changes when you titrate 0.1 molar HCl with sodium hydroxide. 0.1 molar HCl has a pH of 1, and you can calculate as you add small amounts of NaOH what the new pH is. We've done problems similar to that already. The thing is, when you get closer to the equivalence point, which is shown on this graph, you have gotten to the point where if you just add one more drop of the base, the pH change becomes almost vertical. And that is the point that always happens right around the equivalence point. So in a titration, if you're just before the equivalence point and you add 1 drop of sodium hydroxide, the pH will all of a sudden shoot all the way up to the top of that vertical line. The pH change interval of methyl red is shown there, and also phenolphthalein. You can see that either one of these will work for this titration because you're going to be able to see a color change within 1 drop. You don't have to be exactly at the equivalence point. All you have to be able to do is see the color change when you add the drop. So any indicator that has a color change on the vertical part will work for this titration. The situation changes, though, if you use a weak acid titrated with a strong base. We said that if you take acetic acid and titrate it with sodium hydroxide, at the equivalence point you get a basic salt, sodium acetate. That means the pH at the equivalence point is actually going to be above 7 or basic. This is a titration curve of acetic acid with sodium hydroxide. If you look at the way the curve works, the vertical area is shorter because you're starting with a weak acid. The question is, if this is the pH changes, will methyl red work to indicate the end of this titration? And the answer is now no. Methyl red is going to change color from red to yellow very slowly as you add sodium hydroxide, and the color change is going to be over by the time you get to the end. The only indicator that's going to work for this titration is phenolphthalein because the color change is on the vertical part, and if you look at the equivalence point, it's at a pH around 8.5, not 7. Let's say you wanted to do a titration with the reverse case. You want to take a strong acid and titrate a weak base. This is a classic experiment. It's called the Kjeldahl determination of nitrogen in a compound. You can digest the compound, turn it into ammonia, distill the ammonia, and then titrate how much is there, and it determines how much N, or nitrogen, was in the original compound. If you want to titrate ammonia with a strong acid, the ammonia is going to start out at a basic pH and go down as you add HCl. The thing is, the equivalence point is going to be at an acidic pH because NH4Cl is an acidic salt. So here's an example graph where you're starting at a basic pH. The equivalence point is around 5.5 or so. And so as you go down, when you hit near the equivalence point, the pH of the equivalence point is acidic. In this case, phenolphthalein is not going to work because it changes color very slowly, and the color changes pretty much over by the time you get to the equivalence point. The only one that's going to work in this case is methyl red because it's on the vertical part of the curve again. That's the reason why people want to titration or want to calculate titration curves, and that's why you do them in analytical chemistry, because it helps you plan how to get the correct results from a titration. So this has been our discussion now of buffers. You have all the information you need for exam number 2. The class that we do in the next lecture is going to be a different topic. That's the first thing on exam 3, and it's going to be a topic that's not about acids and bases, but we're going back to precipitates.